Hello, Dr. Raj and Scott. I'm the leader of Team B. My name is Ling, and with me are my two teammates, Anthony and Shaodi. Today, we're going to present to you our project. The name of our project is called System on Chip Parallel to Serial Communication with Configurable Protocol. Our macro will be placed onto FPGA or a microcontroller. The motivation behind our project is that we want it to be easy for beginners to use, and we want it to be flexible for industrial use.
Hi, this is Anthony. Here you can see the diagram for our chip and all its inputs and output pins. We have V in, 5 volts. We have clock, 20 megahertz. We have the enable and the write to our SRAM, our input buffer. And we have a set and reset for the road decoder of the buffers. Reset clears all the flip-flops we use in our road decoder, while set sets the initial addresses or word lines. And then we have our data in, which is 10 bits. The reason we use 10 bits rather than 8 bits is because in I2C, start bit and stop bit can happen at any time, so I needed the user input to indicate when they want a start bit or a stop bit to be generated. The next pin we have I2C acknowledge, which is for in read mode. The master is the one who acknowledges or not acknowledges. And the next is to load the bit into the I2C acknowledge. And then the outputs down here, we have I2C slave not acknowledge. This is the pin that indicates during a write mode that the slave device that the master is writing to did not acknowledge the byte, and therefore it terminated it by generating a stop bit. And then here we have a data receive, which indicates during receive mode that 8 bytes of the data in our data out is valid and that 8 bits have been received. On the top, we have the configuration and the load signal to load our configuration. We use 2 bits. We have a disable mode, an I2C mode, an SBI mode, and a UART mode. And here are the output pins for the bus of our protocols. We have the SDA line, which is the input output for our I2C because I2C is half duplex. And then we have the clock, the SCL, which is the I2C clock name, and the SCLK, that's the SBI clock. And next we have the master out slave in for the SBI, sorry. And the transmit for UART. And then we have master in, slave out, and receive, which is for SBI and UART as well. And lastly, we have slave select, which is only for the SBI. Next, we have our block diagram for our chip. We have our clock divider, which takes our 20 megahertz clock and divide it to the appropriate rates for each of our protocol. For I2C is 100 kilohertz. UART can be done in variable time. I think right now is 20 megahertz for our UART. SBI is at 2 megahertz. And then we have the master controller, which controls basically the transmission gate of our various nodes, because there's basically 3 blocks connected to one node in a lot of cases in our block diagram. And then we have a voltage regulator, which creates a 3.3 volts from the 5 volts and also a 1.2 volts from the 5 volts. And it's also used for our level shifter. So what we do is we have our 5 volts that gets converted to 1.2 volts to run our circuit, and then a level shifter that brings it back to the 3.3 volts of each protocol. We have our input buffer which stores up to 32 words, each of 10 bits, 10 bits as I mentioned earlier. And then we have a common circuit block which has all the circuits that each of these protocol can share. including counter, shifter, transmit register, receive register, and other little logics. And then we have the individual blocks, which have the protocol unique circuits, I2C, UART, SPI, and then everything goes into a mux and a level shifter that gets output the correct wave at 3.3. So as you can see, some of the internal signals we have is obviously the divided clock that goes into each of the protocol, and then the change voltages that goes through each of the protocol, the control signals that go through each of the protocol, and we have the data from the buffer going into the protocol blocks, and then the protocol blocks would generate a finish or busy signals to indicate when to advance the row decoder in our buffers, and then our buffer returns with the data ready to tell the protocol blocks when a data is ready and valid. Okay, now let's get into cadence. Here you have the symbol for our overall top level chip. It's the same signals as the the chip diagram I showed you earlier. And if we go in, we have our chip basically with all the blocks in it. So here you have the LDO, the clock divider, the SRAM buffer, some protocol select is basically just 3 transmission gate to control which of the signal from the protocols that go through. We have one for the busy or finished signal that goes from protocol to our buffer, and then we have it for all the data outs. And then here we have the master controller, which controls all the signal for the transmission gates, and the mode of the device. And we have our I2C, the SPI, and the UART. And here's more transmission gates and mux that controls the output signal, and the level shifter that converts our 1.2 waves to 3.3 waves. Let's first take a look at the master controller for our chip that controls which signal goes through to which node. Let me pull up the notepad so it's easier to see. So it's a very simple controller. Basically it's a kind of like a state machine. So here's all my state: the disabled state, the I2C state, the SPI state, the UART state, and then all my outputs, the I2C reset and start, which is to turn on and off the I2C block, and then the I2C enable, which is turns on the transmission gate for the I2C. Similarly, SPI's resets to control the SPI block, and then the SPI enables to control the transmission gates that lets the SPI signal through. UART's the same as SPI. So every positive edge of load or every positive edge of restart, check for restart first. If it's restart, the state will always be disabled, and all these, the start will be 0. My I2C is a high reset, so it'll be at 1, so it'll be at a reset state, and the enable will be at 0, disabled. SPI and UART are a low reset, so they sit at 0, while the enable also sits at 0. And then if reset is not high, then it checks first it updates the state register from the input pin. The input P select, it updates my register state to the correct state, and then through case statements, it just checks for what state the chip is supposed to be in, and then updates the signals. I added a delay here because I want the nodes to settle before I start my protocol blocks, and then that's it. The default is at disabled state. So then there's the disable I2C, SBI, and UART states or modes.
Hi, Professor Roger and Scott. This is Shaodi. So I'm talking more about the clock divider and SRAM. So let's go inside see our clock divider. So this clock divider can use for divide by 10 here, the output here, and the clock divided by 200 because our input clock signal is 20 megahertz. So it's used for UART, and after being divided by 10, it's 2 megahertz is used for SPI, and after being divided by 200, it's 100 kilohertz is used for I2C. So for this one, it's my output, which signal is clock signal divided by 10. So I'm using counter which counts to 5, and toggle mode D flip-flop here, which can make sure the output clock is 50% duty, and it's divided by 10. So I'm using two of this module here, which output here is divided by 100, and toggle mode flip-flop here. So make sure it's divided by 200 and 50% duty clock signal. So let's see my SRAM. So the SRAM we use here is 32 by 10 bits. So let's go inside and see. So this is our SRAM core, and bitline header here, which is for writing bitline header and reading bitline header, and this is the write driver and the sense amplifier here. So this one here is our writing decoder, and this one is our reading decoder. So I'm gonna talk about SRAM core first. So each core here we are using 80 SRAM. So it's based on 60 SRAM, but we add two MOS here, which can help us do the writing and the reading in the same time to make our SRAM faster. For the writing decoder here, we are using 32 D flip-flops here. So in the beginning, the old flip-flops will be reset to 0, but only one of the flip-flops will be set to 1, and the output will connect to the word line, the writing word line. So in each time, the just only one of the word line in the 32 by 10 bits SRAM core will be enabled, and the data will be written inside that line of 10 bits SRAM. So we don't need any like writing address, because after each clock cycle, it's the one here which was here will loop to next one, and to the next one, and this one, the input D from here is connect to the last one, so it will be looping. And we also have a disable writing signal to disable the writing, because if we do the reading and the writing in the same time, sometimes it will cause conflicts when they are reading and writing in for the same address. So in this case, we will disable reading or disable writing. And this is our reading decoder, which has the same structure, a bunch of flip-flops, and also those inverters is used for optimization of the fan out. So this module is used for communication with the transmitting module. The finished signal is the output from the transmitting module, and when posed to high, the address will move to the next one. And this flip-flop here is used for a delay time, because when the address changed, when the new data comes from the SRAM to FIFO in the transmitting module, it will take some time. So we need this delay module here to make sure after the data is already inside the FIFO in the transmitting, so this empty signal will pause to high to reset the transmitting clock divider and enable the transmitting. So this is the writing driver. This structure is very easy. So each one connect to the bit line and the bit line bar. So this when the enable is high and the data when the data is low, so this one will be enabled. So the bit line will pause to 0, pause to ground. And this is the bit line header. So each one here will connect to like writing bit line bar, and the reading bit line. It's like doing per charge every time. So when the enable here is low, writing bit line and the writing bit line bar will pause to high to VDD. And there's also a reading enable signal here, which when it's 0, it will make the reading bit line too high. So there's also one thing in the SRAM I need to see. It's for the bit line header, it needs a reading enable and the writing enable signal. So the writing enable signal is coming from user, but the reading enable signal is coming from the transmitting module. The transmitting module only output the finished signal. So we use the same signal here. After adding a delay part, it becomes the reading enable. So when the finished signal comes here, it will update the address here. May the address be ready here. Finished signal is high, so after delay, the reading enable post to high. So the per charge is disabled. So and then it's gonna be reading. So after some tests, we add like 6 inverters here to make sure it works. And also for the disable reading and or disable writing conflicts detect module here, I'm using a lot of NANDs and AND gates to implement this. So what I did is using like writing 13 and reading 14. Writing 14, reading 15. If both of these are 1, which means there will be a conflict. So when these are 1, so this will be 0. So for this line, we'll connect to AND gate, and the output must be 0. So it will make the output to be 0. So when the output is 0, it will disable the reading or disable the writing.
Hopefully you guys are still awake because I already fall asleep. So let's go into my LDO. I made 2 LDOs. One of them is for 1.2 volts for our circuit to run, which is to reduce power. The other one is a 3.3 volts that will be used with my level shifter for protocols because that's what they use. Alright, I don't want to bore you guys with any details of LDOs because Scott taught me how to build this. Thank you, Scott. And all I want to discuss is what I learned from this. I learned that I suck at building analog circuit, and I also learned that this resistor here is huge. It's 440 kilo ohms, and a better way to build it is to build another circuit mentioned by Scott, but I didn't have enough time to build it. So basically, there's a current mirror here, and this second stage here increases the gain, which is something that I learned recently. Alright, backing out to the top view, the difference between my 1.2 volt and my 3.3 volt LDO is if you go into the air amplifier, you can see that this one has a simpler structure comparing to the 1.2 volts. This one right here use an MOS current mirror and then a gain stage, whereas in the 1.2 I use PMOS, a PMOS as my current mirror biasing source. The idea of this is easy. There's nothing much I want to talk about that. And I want to talk about my level shifter, if I can find it in here. Ah, here they are. So my level shifter, of course, takes in 3.3 volts, and then depends on what the input voltage is. It will either output a 0 volt or 3.3 volts for the protocol used. It's very simple. And also, thanks, Scott. Thank you again for teaching me this. Yeah, and that's all I had to say about my parts.
Hi, me again. I'm here to talk about my I2C block. So here we go. Let's go in it. So as you can see, there's a lot of components here. I'll just briefly describe what each component does. Here on the top, you see we have a counter. Basically, it's for counting 8 bits. It goes from 0 to 7, and at 7, the shift done will go from low to high and stay high until it is reset. So this is used for like a flag for when I'm transmitting. Here we have acknowledge detect. This is to detect and acknowledge or not acknowledge signal from the slave while I'm transmitting. So usually on the 9th cycle, if you include the start bit, if there is a start bit, the SDA line is released by the master for the slave, and the slave on the 9th cycle needs to pull the SDA line low for acknowledge or keep it high for not acknowledge during a high clock during the 9th cycle. So that's just, there's some logic that just detects it and goes through a flip-flop and stores it there. And here at my output signal, you can see there's 4 blocks connected to it. And each of these blocks actually have a, you don't see here, but each of these blocks have their own transmission gate so that they don't fight each other. So we have the start block. I won't go into detail of what's in it, but basically for I2C, a start signal is when the clock is held high, the SDA line goes from high to low while the clock is being held high. So this block does that. I accomplish that with very basic logic. When clock is low, keep it at high, and when clock is high, keep the SDA line at low, and then I accomplish it to make it happen during when clock is high by just adding a bunch of inverters for delay. Ideally, I should have had Shaodi divided my 100 kilohertz clock by half again, so that I can have a clock where the period is half of my current clock, and then that way I can enable the logic in the middle of a high clock. But at the time, I just added a bunch of inverters to create a delay so that this logic would happen while the clock is high. A stop block is very similar to a start block, but instead, when the clock is held high, it goes from low to high rather than high to low. So I did this same thing, basic logic with a bunch of delay. And then the shifting block, that's just a very basic shifting register with a mux at each flip-flop, where the mux is controlled by the signal called load. At high load, the mux will load in the data, the data coming in. At low load, the shifting register will just shift. So it either loads data or shift data. And then lastly, this is for reading in I2C. During a read, when you go from write to read mode in I2C, the master is the one who generates the acknowledge. When the master acknowledges, the slave sends the next byte. When the master does not acknowledge, that's the end of transmission, and a stop bit will be generated. So this is just something that either pulls the SDA line low or high at the appropriate time, which is controlled by my controller. So, and at here, let's go into this. So basically, the way I implement my data in my SDA line is, in I2C, the bus is always held at a 3.3 volts. And so when I want a 1, this NMOS just remains off. And when I want a 0, I turn on the NMOS, and then I will have a 0 in my SDA line. Clock is similar to that, but instead of a data bit at the NMOS, it's just a clock at the gate of the NMOS. And then I have this clock stretch signal, which is a mux, which basically keeps my clock line at low when I need extra cycles to process data or I'm waiting on something. Other than that, it's just my clock. And this is just a transmit register. It's just 10 flip-flops. First flip-flop's the start, last flip-flop's the stop. The middle is the data. Okay, and lastly, actually, this is a register that's for reading. So it takes in the data from the SDA, from the slave, and then shifts it, and then my counter goes along with this shifting register, and when it shifts in 8 bits, my data received will go to high, and this will be, instead of shifting, it'll turn into hold. It'll hold the data until the user is done with it, and it's ready to read another byte. Okay, then the biggest block I have right here is the master I2C controller, which I've written in Verilog, and I'll show you my notepad. So there's a lot of things in here. Oh, this is the wrong. Sorry about that. I had the wrong Verilog file open. So here you have the controller for my I2C. There's a lot of inputs and outputs, so all the inputs, the clock, the reset, the enable, data ready, that's from the buffer. Start takes it from my transmitting register. Start bit from my transmitting register. Shift done, that's from my counter. Acknowledge is from my acknowledge block. Read write. So when you generate a start bit in I2C, that byte is supposed to be the slave address, and the slave address is 7 bits. So the 8th bit is a bit that indicates if you want to read or write. So then this just takes basically the 9th bit in my 10-bit transmit register and as a flag for, if I want to read or if I want to write. And this is the input for in read mode when the master needs to wants to acknowledge, it puts a 1 into this pin, and then the load goes from low to high, and then it'll load the bit into the register, which is used for generating acknowledge or not acknowledge during read. And then the output finish is to let your SRAM know to advance. Load, that's for loading my transfer register. Start, so generate a start and enable my start shift load to basically load my shifter. Counter reset, that's to reset my 8-bit counter. Shift enables enabled my shifter. Stop generates, generate stop, and then enable my stop. And then SDA is to basically release the SDA line when in read mode, or during acknowledge from the slave. I need to release the SDA line. So if I enable this, the NMOS will basically be off, and the bus will be released. Clock stretch is for stretching my clock when I need extra cycles to process data or wait on something. And this is the output for when the slave did not acknowledge at the 9th cycle successfully. And hold, that's for holding data, changing my shifter from a holder, just a normal register, or a shifter. Data received, that's an output to let the user know that 8 bits have been received. And this is just an acknowledge symbol from acknowledge signal for my master acknowledge. And here's just all my states for my controller. The register for each of these outputs, and then a clock at positive edge clock. So I2C is the data have to be valid at high clock, and including that includes the setup time and the hold time. So my state machine updates every rising edge, and while my circuit positive edge, the I2C needs to be stable at high clock, including the hold time and setup time. So my state machine updates all the signals at a rising edge, but my circuit outputs or changes the outputs at a falling edge. So that way, when the clock goes to a falling edge, the data gets updated and is ready before the clock goes high. So then I have a bunch of states: idle, the load state, the start, shifting state, acknowledge state, wait, which is basically when I wait for my acknowledge, stop state, a read state, master acknowledge state, and a read finish, and the default is idle. I won't go into detail of what each state does. It's pretty self-explanatory, and I have a comments in my code. And that's it for my master I2C controller, and that's it for my I2C.
Okay, so it's Shaodi again. So I'm gonna talking about my UART module. So for my UART, it has transmitting out serially and serially receiving here. So this is the data in coming from the SRAM and the clock, and the empty signal from SRAM, the reset from global. So it's the data out, which comes from the data coming from the receiving. So it's serial inside, and will make it a data frame 8 bits, and comes out here. So this queue is only for testing from the counter inside. So this finish signal will go to the SRAM. So let's go inside. I'm using this transmission gate to control the clock. The clock goes in, or clock is off. So it's controlled by this one and this one. So the control is a little bit complex. So when the receiving is enabled, so the clock will will enable this transmission case, the clock will goes in and everything is on. And otherwise it will disable this one. So the data comes from here. So flip them first, because when there's no data, when there is no data here, the line will post to high. It's all high. So the start bit is 0. So I want flip this first, and so which means the start bit will be 1 here. So if there's no data, it will be 0. So it comes here, and this is a shift register. So it's like a pipeline goes the receiving data, and after when the first data, the start bit goes to here, the 1 goes to here, and it's the enable signal will be high, and after delay module, the reset will be high. When the reset is high, it will make this one reset immediately without the clock. So the enable will be 0, and the reset be 0, and do nothing. It's always output 0. So we take a look at this flip-flop. So yeah, I'm using a false mouse here. When the reset is high, so it's supposed to, the output will force to 0. And when the clock is low, so the clock is low here, so it's 1 here. So the clock is low and the clock bar is high. So for this latch, when the clock is low, so this one will be on. So when this one is forced to ground, so the ground comes in, and the ground will be stored in this latch. Alright, so when the reset is 1, it happens in a very short time, so it will disable the clock here, and yeah, it's disable everything, and also reset the FIFOs here. But before that, the data is already comes out here. So this clock is also from this clock. So when clock is disabled, so the transistors here is disabled. The flip-flops here is disabled, so the data will be stored inside. And you choose which one you should output. So that's the receiving part. So this is the transmitting part. So the data and the empty comes from the SRAM. The reset for the global, and this is clock. So the finished signal goes to the SRAM. The transmitting signal in serial. So let's go inside. So the data from SRAM comes here, goes to the registers here, and you just select which one goes out. And this is the transmitting FIFO, 8 bits here. It's for data. So this one is for start bit, and this one is for stop bit. Because the stop bit is 1, so it posts to high, always. And the start bit is 0 when it's reset. So, and this one is because when the data, there's no data here, it will be all VDD here. And this one is counter. It counts to 10, and it will stay at 10 until it has a new reset signal here. It will reset to 0. So when it is 10, it will output finish signal. So for this part is the control from the SRAM. So the empty is from SRAM. So when it's high, the clear bar initially is high, so it's high here. And when the F1 is high, this is high. So it's 1 and 1 here. It's output 1. The reset, when the reset is 1, so it will select the this registers these FIFOs to cut off this line, cut off the writing, and start to be a shift register. So let's go inside. I'm using a mux between two D flip-flops. So when the C, which is from the outside, which is from the reset signal, when this is high, so I choose B here. So it will be a shift register. So when it's 0, it will accept the data comes from the outside. Okay. So this is my transmitting part.
Now I will continue on to talk about my SPI module, but before I proceed, I want to show you what the waveform looks like. So SPI has 3 outputs and 1 input. The 3 outputs are slave select, clock, master out, slave in, and the 1 input is master in, slave out. So basically what happened is whenever the device wants to talk to a certain slave device, it will pull the slave select line low and then generate the clock and then send out the data. And when it wants to receive data, it will do the same thing, except for it will send out some junk data and it will receive the data back. The master out, slave in, and master in, slave out pins are connected in a way like a circular buffer. So to get data back, you just send some junk data. Now let's go into my SPI module. It's fairly simple. Right here we have shift registers with mux that's controlled by a signal. So basically when I'm loading data, the mux will the mux will be 0 and select it to load in the data, and when I want to transmit the data, the mux will be 1 and then transmit the data out to master out, slave in. My protocol only sends out 8 bits of data, and since our SRAM uses 10 bits, I chose that I want to use data 0 bit as my enable signal for my tri-state buffer. So when the user wants to receive a signal, he chooses the data. He puts bit 1 into data 0, so that whatever the output or whatever the input of master in, slave out is, it will become the data out that goes to the chip. Then I have I have a counter that counts to 8, and then once it reaches to 8, we'll send the finish signal to the SRAM. I also have some simple logic, and I have a counter reset. So the idea behind it is fairly simple. My SPI only works for certain mode, but it works and the result is good. I would like to show you our simulated results, but unfortunately it's very time consuming to run those simulations. Every single unit in our macro works individually. Some of them, like UART, works with SRAM, but some other modules have problems running with other components.
Hi, so I'll finish our presentation by just briefly going our market and cost analysis. So as you can see, this will be in the report. The non-recurring cost is about 1.3 million. Most of it comes from cadence licensing or rental. And the manufacturer costs in the end that we calculate, hopefully I did everything right. These are what I followed in lecture 8, is about $5.49 per chip. So after some research and discussion, we concluded that it'll be much more profitable if we just sell our physical chip rather as a licensing for IP, because there's only so many companies that will, build and manufacture microcontroller, and so many FPGA manufacturing microcontroller. So we don't think we can sell a lot of license. But then by selling the chip itself, there's a lot of units, billions of units of microcontroller and FPGA units that are being shipped out. So if we're to sell the chip itself, we think it'll be more profitable than selling to the few companies that would want our design. Because, even though this one company builds like hundreds of different microcontroller, they would essentially basically need one license. But if we were to sell the chip itself, then we can take advantage of one company's hundreds of microcontroller, or basically the billions of units of chips they would need. So that's our conclusion for our market analysis, and that's it for our presentation. Hopefully it wasn't too long and boring, and hope you guys have a great summer. Thank you.